Okay, so good morning. So this is a short lecture on uh, essentially the same quantum mechanical problem of the beam splitter, and we are going to see it from both perspectives. We are going to see it from the sum over paths formalism of probability amplitudes, as well as the the usual way we describe the evolution of a quantum state vector. So this is our Max Render setup. So by the way, this uh, the homework problem is also, I posted the solutions. So essentially what's happening is the following. This is your mode 1 where, and this is your state vector when, so I'll call this mode A, I'll call this mode B. This is when the light is entered from the down port, it hits the beam splitter and it takes these two paths. So this is my beam splitter 1, this is my beam splitter 2, and essentially, as we see from the postulates of quantum mechanics, this is evolution that's going to be represented by a unitary matrix. So let me write the beam splitter 1 as a unitary matrix. So this is a 50-50 beam splitter. What it essentially does is to the state 1, 0, it's going to give me the state, and to the state 0, 1, this is going to give me this guy over there. So essentially, when I start with light in this state, through the action of the beam splitter, I get an equal superposition of something going in the upper port, also something going in this way, this direction. So that's the action of the first beam splitter. We'll ignore the action of the mirrors. Essentially, the mirrors are going to put a phase difference, but since it's a balanced Mach Zehnder interferometer, both these paths, this path and this path, are going to acquire the same phase. That's not going to matter. So just let's consider the beam splitter 2. What does it do? Essentially, the action of the beam splitter 2 is exactly the same. So I'll just call it as beam splitter 2 is beam splitter 1 is this given by this unitary matrix. So what does it do? This is 1 over root 2 iota. Again, I'll apply the beam splitter on this state. So essentially 1, 0 after the action of the beam splitter goes to this guy. So now I'm going to apply again the beam splitter on these two. This was the first beam splitter, then the second beam splitter. So I0 will again go to just plugging in the action of the beam splitter. and 0 1 goes to uh, this guy. And when I solve it, the answer I get is 1 by 2. 1 by 2, sorry, it's between minus 1 by 2, 0, 1. This is just algebra. You can do it. 0, 1. These two paths cancel out. I essentially get iota 0. That essentially means that after these two beam splitters, all the light I detect is in one of these guys. It's going to be iota 0. And this detector has no amplitude. So one way to see this was from sum over paths. We are trying to sum over all possible paths from A to B, and the paths leading to detector D2 in this case destructively interfere, and the paths leading to detector 1, the contributions constructively interfere. So this is using the usual language of quantum mechanics, where this was your state vector and the beam splitter was the unitary evolution. Essentially, the same thing is happening in the picture of sum over paths. So for that, what do? Let me again take my setup over here. So essentially, what's happening in the path integral picture, let me call these as states 1 and 0, where 1 is this guy, 0, 1, and 0 was when all the light was in the upper port. So here is the flow of time, you can say. I encounter a unitary operator at some time instant. This is my the beam splitter time, let me call it T1 out here. And these paths bifurcate. So I have this guy and this guy. There's light both in upper port and lower port, and there are going to be coefficients associated with it. What are the coefficients? I have iota over root 2 and 1 over root 2. Okay, very good. So now at this point I encounter my second beam splitter, BS2. So this was BS1, this was BS2, and my paths again split. Path 1, and I also get these contributions over here. So what's really happening is that if you look at it, this was one of my paths. So this picture has all the paths. Let's say this was my path 1, one path, this was second path, then uh, I have this as another path, and this is the fourth path. And if you look at it, I have essentially all paths. So I have one path, I have second path, and I have this third path, and I have this sort of fourth path over here. Now, the way I evaluate it is that I would be just the transition amplitude from point 1 to point 2 will be given by these coefficients. What's the probability when I encounter one beam splitter? What's the probability from going from state 0 to state 1? That's going to be iota by root 2. Probability amplitude, I'm sorry. Let me just erase it since I've already told you what the paths are. Yeah. So from going from 0 to 1 is 1 by root 2. Similarly, when I'm here on this beam splitter, this is 1 by root 2. This coefficient is iota by root 2. That's just coming from your matrix multiplication. And so that essentially is the idea over here. So when I start with the state 0, 1, all I do is that I sum over all the paths. So, well, so this path was probability amplitude was iota by root 2, and from going from 1 to 0 was again iota by root 2. Okay, so now if I calculate the probability of going from the state 0 to the state 0 over here, is going to be the sum of these paths. Path 1, also path 2. Now what does it sum up to be? I just multiply the coefficients over here. Yeah, so this was again 1 by root 2. So I get 1 by root 2, 1 by root 2, 1 over 2, and I get iota by root 2 times iota by root 2 minus 1 by 2. So these two paths destructively interfere. I'm going to color one of them by red to show that red and black destructively interfere. This path and this path, I have destructive interference. Interference. However, from 0 to 1, the two paths I have this path and this particular path. I get both of these amplitudes are going to be iota by 2, 1 over root 2 multiplied 1 over root 2 and 1 over root 2 iota root 2. That's going to give me for this is my part number 3, this is my part number 4. So paths 3 and 4 have constructive interference. And hence I get probability of 1 on the detector D1. Detector D1, this eventually goes to detector D1. Detector D1, 100% probability of detection. So the message I want to give you is that this matrix mechanics using Schrodinger's equation, unitary evolution, and summing over all the paths with probability amplitudes where I'm going to chop up the part into this, where the probability amplitudes of all the stages multiply, and then individual path probability amplitudes after that multiplications adds up. Essentially how I compute the path integral kind of a thing. They are exactly the same thing, and in fact you can see this through some sort of a matrix multiplication. For example, when I multiply two beam splitters. So what's essentially is happening? I have a state 1, it goes through beam splitter 1, it goes to beam splitter 2, and finally I have 0. And I saw this in terms of the constructive and destructive interference of paths. I can just see it through the multiplication of these two beam splitter matrices, which is essentially going to be 1 iota, iota 1, 1 iota, iota 1. So that gives me yeah, just try to do the math yourself over here. But essentially, that is the idea. Yeah, so this is going to be. So this is the action of beam splitter 1, beam splitter 2, this matrix. And essentially, we could just replace beam splitter 1, beam splitter 2 by this matrix. I'm calling it M1. So this is a ket 1 going through M1, which is the joint action, just a matrix multiplication. And what do I get? Well, this is 0 iota iota 0 applying on ket 1. So 1 by convention is this guy and 0 is this state. So when I apply it to 1, my final state is going to be just the inverted state with, all the probability in the detector D1 over here. So I'll just make it all I can. Yeah, let me just separate this figure. That's going to be iota 0. So that is essentially happening. Everything goes in this particular guy. Just going to make it a bit neater. Yeah, so essentially, if you can look at it, this matrix multiplication is just nothing but sum over all these paths. Entire information of this matrix mechanics, this matrix multiplication carries all the information of the path computation we do. So this is a very powerful formalism. Mathematically, it's convenient for us to multiply propagators and matrices to get the answer automatically. But as we saw, there is so much richness in the journey of a single photon. Conceptually, it changes a whole perspective, and we actually appreciate and see the power of quantum computation or quantum mechanics, which is very counterintuitive to us, through this sort of a path integral formalism. So I hope now it's clear whether I deal with the summing over all the paths or I deal with unitary evolution, matrix multiplication, Schrödinger's equation. They are exactly sort of equivalent formalisms. So we'll be studying another such example when we are going to do the search algorithm. But I thought this would be relevant to you guys. Thank you.